So welcome to our April monthly meeting. The second of our webinars that we have done so far. During this pandemic, the Georgia ITE board and the volunteers are working diligently to make sure that we can continue to offer as many technical events during this time of quarantine and social distancing as possible by utilizing our online resources, including the website, Facebook, LinkedIn, Twitter, and YouTube, and now MS Teams. Today we are testing MS Teams out as a new option for this remote social distancing technical session. So please, if you see, or well, don't see, if you communicate with anyone that's on the board or that is a part of setting up these webinars, please let them know how awesome they're doing, because we're very impressed with what we've been able to accomplish over the last few months. I'm guessing a lot of you are wondering about summer seminar. We currently have an open survey through the end of the week to get a feel for everyone's opinions about how they're feeling on the upcoming annual trip to St. Simons. At this point, we're working with the summer seminar committees and the hotel to determine what our options are and the best way to proceed with summer seminar while keeping all of our members and guests safe. It's likely that this event will be modified, but we are doing everything we can to hold it in some way. That's probably going to mean restricting some of the registration to meet social distancing requirements. And we are looking at ways to be able to include additional people remotely for both the technical sessions and for social events. Like I said, we're doing everything we can to make sure that something for summer seminar happens, even if it's not in the format that we're all accustomed to. Additional committee announcements and updates from the board are going to be sent out in the e-blast, because I'm sure a lot of people aren't on yet and aren't getting a chance to hear these. So let's move on for the presentation today. Like I said, we're testing out MS Teams as an option for this webinar format. For this event, please make sure that you remain on mute and that your video is turned off throughout the presentation so that random videos don't just pop up. We are recording this and are going to put it on our YouTube page for future viewing. If you would like to submit a question during the presentation, please type it into the chat feature for those to be answered at the end. And everyone needs to remain on mute. So now we're going to turn it over to our presenter. Possibly.
Yeah, that will be me, probably. I hope everybody can hear me. And I hope my presentation will start.
I'm going to have him introduce himself today because I don't have his bio in front of me.
All right, I will do that.
Please welcome Jaap Tigelaar on Turbo Roundabouts.
Yeah, thank you. I hope you can hear me.
And we'd like to thank our sponsor as well, Jacobs, for sponsoring this monthly meeting.
Okay, thank you. Yes, Turbo Roundabouts. First, a little bit about myself. I'm Jaap Tigelaar. That's how you pronounce it well. No problem with that, by the way. Born and raised in the Netherlands, so this accent you hear and the struggling sometimes I have with words, that's because I'm Dutch. I did my Master of Science at the Delft University of Technology in the Netherlands, of course, and joined Arcadis in the Netherlands already in 2008. So I'm already one of the older. In 2018, I heard that the Federal Highway Administration was talking about the Turbo Roundabouts in the US. And that would be as a new development over here. And because the Turbo Roundabout was already a tool in the toolbox in the Netherlands, I used the Quest program from Arcadis to come over to the US to give some presentations about the Turbo Roundabouts. With that Quest program, Arcadians can travel to other countries to exchange knowledge. So I used that to introduce the Turbo Roundabout over here. And when I was over here, I found out that we, as Arcadis, had a great group of people here working on interesting projects. And at that time, I saw, well, why not change locations and make a move to the US and join Arcadis in the US. So since February 2019, I am located in the Atlanta office working on US projects over here. For today, I'd like to touch some of the topics, dig into a little bit of the evolution of the roundabouts in the US, also discuss why turbo roundabouts, what is it, a little bit of the history, looks and feel, how do they look, dig into some of the details of the design aspects, look into the traffic flows and capacity, look into the special users like bicycles, how do they use the turbo roundabouts, and touch some of the aspects you need to have for the implementation in the US. And of course, afterwards, there's a question and discussion possibility. So get into the roundabouts. The roundabout journey in the US already included the simple single lane roundabouts. And we got them down pretty easy to design. We use them in urban and rural areas, low speed and high speeds. And after that, we blew them up to the multi-lane roundabouts. And we saw some interesting topics handing over and problems handing over to the double lane roundabouts. That's what we touch later on. After blowing them up, we also shrink them to the mini roundabouts. They work well in residential and low-speed commercial areas. But what will be next? And what's the next tool in the toolbox? And can there be another type of roundabout? And I think there might be. And that's the turbo roundabout. That's the typical Dutch solution for the multi-lane roundabouts as we use in the Netherlands. So why the turbo roundabout? Well, in the 80s in the Netherlands, we introduced the single lane roundabouts. And since then, we built almost 8,000 of them. And like in the US, they were very successful in the Netherlands. But with the increase of traffic and traffic volumes, the single lane roundabouts reached their capacity and we replaced them by the multi-lane roundabouts. But this was not by the increase of the capacity. We did not see that the capacity doubled, and we didn't keep the same safety improvements as we had with the single lane roundabouts. We saw some fender bender pressures. You can see people using the inside lane, hitting cars in the outside lane when leaving the roundabout. This issue we saw happening in the late 90s in the Netherlands, and this is similar what we're experiencing in the US right now. So this movie illustrates two of the common error drivers can make on the multi-lane roundabouts. The green arrow car enters the inner lane of the roundabout, and you can see the red arrow car also want to enter, but not yielding for all vehicles in the roundabout. It has to yield for all lanes at the roundabout. We forgot to do that. So that's the first mistake, failure to yield on entry of both of the lanes at the roundabout. When they continue, you can see what else is happening. The mistake number two, the red arrow car driver is at fault for failing to obey the lane use signs. So, and choosing the incorrect lane. So he crashes to the car in the inner lane. So when you want to make that left turn as that red car wanted to do, you needed to take the correct lane, and that was the inside lane and not the outside lane. So two of the basic errors you can see happening at the multi-lane roundabouts. And that's that safety issue we try to resolve with the turbo roundabouts. So we had a challenge, design a layout which eliminates the safety conflicts, but still increases the capacity. And that resulted in a spiral-shaped turbo roundabout without lane changing on the roundabout itself. And you may mention why the name turbo roundabout. Well, that refers to the improved traffic flow compared to a standard multi-lane roundabout and doesn't refer to maybe high speeds the turbo sounds like. Basically, we designed the turbo roundabouts to operate with relative low speeds. So what's the turbo roundabout? How different is that from roundabouts we used to design in the US? There are four main concepts on the turbo roundabout. First, there is no lane change within the turbo roundabout. This eliminates the conflicts showed before, and this is accomplished with a small raised curb between the lanes, and we will dig into that design aspect later as well. With this curb in place, drivers are forced to make all lane changes well in advance of the turbo roundabout. This can be done several hundred feet before entering the roundabout. Another very unique feature is the spiral geometry. And you can think of two semi-circles of a roundabout. So you have a double lane roundabout with a little bit of an offset. This offset naturally spirals the inside lane to the outside lane of the roundabout. And lastly, unlike many roundabouts here in the US, the approaches to the turbo roundabout are radial. That's the right angles. This is a very different philosophy on the design we use in the Netherlands instead of what we use in the US. But we will touch that a little bit later. Basically, what we saw was that the turbo roundabouts had a great safety aspect. So by changing the layout of the roundabout, we eliminated a lot of the conflict points at the roundabout. At that left image, you can see a basic double lane roundabout with 16 conflict points, 12 conflict points, 2 weaving points, and 2 cutting points. And the turbo roundabout on the right side, you can see that's only 10 conflict points. So we eliminated the weaving points and the cutting points. And that's a reduction of 37.5% of the conflict points. And the less conflict points you have, the less chances on crashes you have. And that's what we saw also in an evaluation study. One of the students Christian Vos named did a study in 2016, a before and after study. And he looked at several intersection types and 3 years before and 3 years after, and saw the reduction in crashes. So changing a unsignalized intersection to a turbo roundabout, we saw a reduction of 75%. For signalized intersection, it was a similar reduction, 74%. From a multi-lane, double lane roundabout to a turbo roundabout, we saw also a decrease of 53% of the crashes. And also a single lane roundabout transformed into a turbo roundabout, we saw 61% decrease. And that is basically because the single lane roundabout has, you change the single lane roundabout to a turbo roundabout because of capacity conflict. So if you have too much cars at the roundabout, you also have a lot of crashes. By changing and increasing the capacity to a turbo roundabout, we saw also a 61% decrease in crashes. A little bit about the history. Well, the turbo roundabout was invented by Bertus Fortuyn in 1996, and you can see him on the photo below. The guy on the right, it's Bertus Fortuyn, and we met him somewhere October 2018. Since he invented the turbo roundabout, we have already built 372 of them in the Netherlands. And if you take in account also the Aruba, that's 5 additional, so then it's 377. Addition to that, there are about 225 of them outside the Netherlands and basically in eastern of Europe. So what we saw in the Netherlands, this graph showed the number of turbo roundabouts in the Netherlands. First one was set in 96. The second came in 1999. And afterwards, it was about 5 or 6 each year. So you can see the graph is increasing slowly. But after that, after it was proven a success, it really started hitting off with a lot every year. And you can see the graph increasing rapidly. In 2004, the first one came in Germany, and other countries followed, basically Eastern Europe. And outside of Europe, there are only two of them. South Africa have one of them, and also in Canada there's a turbo roundabout. Well, they look like a turbo roundabout. It's not actual turbo roundabout, I think, but they are look-alike. Well, what was for Towns, the inventor, what was his design philosophy? One of the most, so he thought about the roundabout, and he thought, how can we design safety by just implementing the right geometry? And this is the turbo roundabout, and that resulted in a radial design. And basically, a radial design makes the crossing distance, as you can see in the image. That's the colored piece. It's a short crossing distance, and it's basically just crossing one lane. So the crossing area, the conflict area, is small, making it easy to cross, and also that raises also the capacity. And basically, because we have a radial entry, you can also have a good sideline. So if you're still waiting for entering the roundabout, you just have to look slightly over your shoulder to see if there is a conflict coming, if there is another car coming. You don't need to look all the way over your shoulder, and that's especially for areas with a lot of elderly people can be a really advantage. The radial approach also result in low speeds at the roundabout and on the roundabout. And basically that also increases the capacity. So having a short crossing and lower speed at the roundabout, that increases the capacity. So that's beneficial for capacity. How do you do that? Well, that sign, we also implement a sign just in the middle of the roundabout. If you entering the roundabout on the radial approach, you just drive ahead of this sign. And when you see that sign, there's really something you don't want to hit at, so you will brake and you make that corner. So basically, with this kind of signage, you can also design the radial approach, and that's something we don't use a left offset in our designs, and that's a difference as the roundabouts are designed in the US. Well, how does it look like? Well, we have different shapes, and those vary in the number of entry lanes. So the basic roundabouts, as you can see in the left bottom, is we have 2 or 1 entry lane. But with we also have the bigger ones with 6, 7 to maybe 8 entry lanes. Those will be signalized. Those you can see on the right bottom. But also you can vary on the exit lanes. So it's also 1 or 2 exit lanes you can see. And in the left bottom, you can see that's basically a 2x2, similar to a 2x2, 2 exit lanes and at least 2 entry lanes. But also you can shape them special. It's not necessary to have all right angles at the roundabout. So you can also have different shapes in the angles. Also, multiple legs with an oval turbo roundabout are possible. So we design them almost everywhere. And also at some of the interchanges with the freeway, we design the peanut or the dog bone turbo roundabouts. So let's take a drive. How does it look? Entering the roundabout, you see some signs showing which direction you need to go. This car wants to make a left turn, so we'll start in the left lane. Choose the lane ahead. You can see the pavement signs. You can see the median in the elevated lane separation. Entering the roundabout is easy. At the roundabout itself, you are guided through the roundabout. And for the exit, you just use your blink to get out. No conflict at all, and you can reach the destination safely. This is a 80 kilometer, 50 mile per hour road. A bit more into the design. All design criteria in the Netherlands are incorporated in this blue book. That's the national guidelines for turbo roundabouts. It's published by the CROW publication 257. And this is basically based on all Bertus-Fortuyn's principles. The Federal Highway Administration in the US is working on Turbo Roundabouts publications, but these are not guidelines yet. The first publication is the Advancing Turbo Roundabouts in the US. This is an exploration of what you can find in the world, what there is to know about turbo roundabouts in the world. Next publication will be more a technical summary, and that will dig into the turbo roundabout aspects and in a US context. And we from Arcadis are helping the FHWA with these kind of publications because we have a lot of knowledge about them. The spiral design, as mentioned before, the spiral geometry is a key element for the turbo roundabout. Fortuyn created a smooth spiral-shaped vehicle path by shifting the centers of the two-lane roundabouts by a single lane. You can see on the image above. The inside lane then aligns perfectly to the outside lane, and by rotating the whole, the approaches can connect to the right radial angles. This idea looks easy, but for the actual design, the translation axles should be rightly placed on the major approaches to create a similar curvature for all through traffic. And this basic shape is called the turbo block. And there are several turbo blocks designed by Fortuyn, and they vary in the number of approach lanes, exit lanes, and rotary lanes. And because they vary, the suitability for different locations is imminent. As you can see, we have the basic shape turbo roundabout. That's this one with one translation axle. If you vary the number of entry lanes, you can see it's going to be a bit smaller capacity-wise. You can see the blue arrows. It's for a main road with a smaller side road. If you have a high flow for right and left turns in one direction, you can make a knee roundabout, as we call it, with a sort of bypass. And when you have bigger flows, you can translate the turbo block twice with two translation axles, and then you have additional lanes, but with a higher capacity, and basically suitable for two similar traffic flows. How big do we build them? Well, the size is depending on the number of lanes and of course a design vehicle. That's similar to what we do in the US. Typically, we design the roundabouts, the turbo roundabouts, for speeds between 23 to 25 miles per hour. And what you can see, a standard roundabout has the inner radius, the inner field of about just a little bit lower than 40 feet. And the outer diameter varies because we have that spiral layout. We don't have a fixed outer diameter, but that varies. The smallest is 148 feet, and at the largest area, it's 165 feet. Of course, for areas with lower trucks, for example, we design them a little bit smaller, and with a lot of trucks, we design them a little bit bigger. The biggest are about 213 feet in diameter. That lane separation, a key element for the turbo roundabout. This is done by that elevated separation. You can see on the images. That's discomfortable on high speed, but a little bit comfortable on low speed. It's forgivable. So if you hit it, it doesn't kill your car, but you don't want to touch it if it's not necessary. The height of these is about 2.7 inches, and it's about 11.8 inch wide. And we place them just a little bit over 3 inches in the pavement. And this lane separation is helping you guide over the roundabout, so you don't change lanes. Another design aspect of the turbo roundabout is the opening width. That's the location where the lane separations start, and that's crucial for the good roundabout design. The the opening width should suit the situation. We want to keep the opening width as wide as necessary. So most vehicles don't negotiate the curb and can comfortably enter the inner lane. But also you don't want to make it too wide so that people from the outer lane will jump into the inner lane. So on the other hand, you need to keep it narrow. So that's always a fight between make it wide and make it narrow. So we designed a special thing for that. We call it a frog. So that is the it looks a little bit different from the elevated curb, but it's showing, at least when you enter the roundabout in the outer lane, you will not go to the inner lane. But when you drive in the inner lane, you want to go to the inner lane, of course, you can ride over it if necessary. How does it look like? It's like this. It's lower than the elevated lane separation. It's about 12.5 feet long, 3.5 feet wide, and also we place them in the pavement. Next to the lane separation, also the markings and signage are really important for the turbo roundabout, because as we said, you need to choose your lane way ahead of the turbo roundabouts, because you cannot change lanes at the roundabout anymore. So upstream, it's necessary to have clear directions with destinations. So what we do is we place always a signage just in front of the roundabout with the designations, destination, sorry, where you want to go, left, right, or straight. Near the roundabout, we place other signs, and if possible above the road, but sometimes also next to the road, again with the destination for each lane. And next to that, we place at the pavement, we place the directions again, which lane goes which direction. On the roundabout itself, it's not necessary to have signage. We don't put the signage on the pavement. Some road authorities do it, but because you cannot change lanes and you can only exit, you actually don't need them anymore, because it's not necessary, because you can only follow that lane. When you exit the roundabout, we place the destinations again. So when you want to enter, you can see where you can go. When we built the big roundabouts, turbo roundabouts, these are really large with a diameter of 360 feet. These are signalized. They can handle high volumes to 8, 9, 10,000 cars an hour. Speaking about capacity, this is a table. It's in Dutch, sorry for that, but it shows at least a list of the intersection layouts. We have the single lane roundabout, the double lane roundabout, and the turbo roundabout designs, and then signalized intersections. What we have in the columns is a theoretically capacity. That's basically the sum of all approaches, and the practical. So this is based on all the formulas, and this is what we experience in real life. And of course, the entering conflict volumes. What we see is when you look at a double roundabout, multi-lane roundabout, the practical capacity is about 3,500 vehicles. And the basic shaped turbo roundabout, as we showed before, has a similar capacity. If you build them bigger to the spiral roundabout or the rotor roundabout, like we saw earlier with the multiple entry lanes, you can reach 3,500 cars an hour. And when you build the big ones we saw just in the slide before, you can reach over 8,000 cars an hour. And that's pretty high volumes for a intersection. To calculate which turbo roundabout is suitable for the location, we have a tool. It's called the Meerstrooks Rotondeverkenner. That's of course Dutch. In English, it's the multi-lane roundabout explorer. It calculates the capacity in just a simple Excel tool. It compares the various types of roundabouts, from a single lane roundabout to a double lane to a turbo roundabout with the different shapes, and we have them over here with a bypass turbo roundabout, the egg roundabout, turbo roundabout, knee roundabouts, and the rotor roundabouts. And just by adding the capacity, you can see if a roundabout is suitable. And it just takes a look at the saturation rate and the average waiting time. If the saturation rate is below 80% and the average waiting time below 50 seconds, then we say a turbo roundabout is suitable. Otherwise, it's not suitable. So this determines appropriate help to look at the several designs available. If you look at the capacity formulas, this is a graph showing a flow at the mainstream in the x-axis, and the y-axis shows the flow of the secondary stream. And what we see over here, this is based on traffic formulas, that a double lane roundabout, the blue line, operates better with slightly better with a lower speed, a lower flow on the mainstream. Then you can see we operate a little bit better. But when the flow at the mainstream increases, you can see that the turbo roundabout operates way better. And that is basically because of the turbo roundabout has a better lane utilization. Next to that, traffic entering the roundabout are less hesitant because they know they cannot hit on the roundabout, and they have also a smaller conflict area. And that's basically because of that radial approach. Special uses, and we start with the bicycles. Well, in the Netherlands, we like bicycles. As you can see on this image, it's a typical PM peak hour in the city of Utrecht. We have a lot of bikes. In the Netherlands, total, we have 23 million bikes, meaning that is over 1.3 bikes each person. And we don't use them only for recreational traffic, but we also use them for every traffic. Basically, 27% of all trips we make in the Netherlands are by bicycles. Meaning we need to have a great bike safety. And that is, well, we need to have the right bike facility. And that can only be done if we have the bike safety. And the Dutch policy in general is to reduce the differences between mass, speed, and direction. By doing that, you can design safe infrastructure. That's in general, but that's also holding for roundabouts, of course. That means that we prefer separate facilities for bikes and motorized vehicles. Or if there is not enough space available, we keep the speeds as low as possible. And you can see on the bottom right, the street has shared bike lanes with the cars, and we allow only low speeds. This is 30, not meaning 30 miles per hour, 30 kilometers an hour. So that's less than 20 miles an hour. And then we allow shared. But we prefer on the left side a separate bike facility, and even with high volumes for intersections, we do special things with the bikes. For roundabouts, we try to do it, of course, also as safely as possible. In the Netherlands, at roundabouts, we have separate facilities. If we don't have enough space to make a bike path, separate bike path, we at least provide bike lanes. And within the city limits, bikes have the right of way. You can see over here. Outside the city limits with higher speeds of cars, bike must yield for the cars. At the turbo roundabout, well, they have to cross multiple lanes. And at the turbo roundabout, we don't allow bikes. So when we design a turbo roundabout, it's always with a separate bike facility. To cross the multiple lanes, the cyclists can use the median, as you can see on the top bottom. The top right. And they can use the median to cross the full crossing in twice. And we designed that crossing in the median as an S-shape, and that slows down the speeds of the bicycles, but it has an additional benefit that in the middle, bicycles are facing the cars that are coming to the roundabout, so they always have a better eye contact. With higher volumes, we do a grade separation crossing. And the right bottom, we have just a simple bicycle tunnel. But in the left one, we have a bicycle route with a bicycle roundabout in the mid-center. So we do something special sometimes where the number of bikes are really high or important connections to have a safe passage. And next to that, with the big roundabouts we build the nice bridges all over it. But of course, this is really expensive solution, and we only do for special locations. Other specific uses are the trucks, of course. In the Netherlands, the typical Dutch truck is similar to a WB50. That's our design vehicle. And we tested the basic roundabout with a diameter of 165 feet with the design vehicle WB62. And what we see is it takes a little bit of the outer edges. So when you want to design a roundabout for W62, we need a little bit more space, about 180, 190 feet, to provide a better way for the trucks. On the basic shape roundabout, the W40 works pretty well, of course. But in the Netherlands, we also build bigger roundabouts. This roundabout is the 190 feet. And this truck, what you see entering the roundabout, that's a 82.8 feet long truck. It's making the left turn. And as you can see, it enters the roundabout. It stays in its own lane. It doesn't use any other space, no other lane. And it's heading out to the freeway ahead. It's easy and no special things appearing. Of course, this has a little bit of a different layout than the W62 or the 67s. But as you can see, this is also a big truck using the roundabout as it should be. When you build them a little bit smaller, you can add, of course, truck aprons. Easy to ride over for trucks, not so easy for cars. Other special uses are the motorcycles. Well, the main concern we heard in the US about motorcycles is how do they use the elevated lane separations. Those are not ideal for the motorcycles. But what we experience in the Netherlands is that the smaller chance that drivers unexpectedly make a left lane change, not possible anymore at turbo roundabouts, outweighs the risk of hitting the elevated lane separations. So at the end, motorcycles also like the turbo roundabouts better than the normal double lane roundabouts, basically because it's also safer for them. But it's essential to design the turbo roundabouts well, meaning that we have warning signs upstream of the turbo roundabout about 150 feet ahead. We repeat warning signs at the center island, and we don't design the lane separations as shown before, just not too high, just a few inches. And we use contrasting colors, and that's showed at this slide. So what we do is we use the upstream, we put a signage. This means verhoogde rijbaanscheiding, means elevated lane separation. So that's the upstream. At the center island, we have a similar warning for motorcycles. We have the not too high of the lane separation, so that's safe to ride over. And we use as high contrast as possible. To continue, what will be the next steps for implementing them in the US? Because we don't have them yet. We hear some hesitations, but we also see a lot of benefits. Well, what I think is necessary is we have showed you the Dutch standards, and probably we need to have minor adjustment to fit to the US design vehicles. There's a little bit different, people drive a little bit different, meaning that maybe we need to use a different lane width, a little bit a different diameter or something like that. Next to that, we need to calibrate and validate the US driver behavior. That's basically taking care of the capacity issue. Because we drive differently in the US, are the capacity values we showed before, are they different or not? And of course, look at specific conditions like drainage, or when we had a presentation in Florida, it was all about hurricanes and how do you put the signs on top of that. In north of the US, we had discussions about snow plowing. Well, everything we can address, but you have to look at those conditions and show them what kind of solutions are suitable for that. And of course, because of people are hesitant, it should be you should have a proper introduction of the concept. People need to understand how to use it, how the concept works, and why it's safe and better. If you have the first one, of course, we need to monitor it and evaluate the driving behavior and traffic safety and traffic flows. But that's only what you can do at the end when there's already one built. And first of all, start with a simple turbo roundabout. Don't do the big ones as we showed before, or maybe just introduce some of the turbo roundabout aspects. Maybe just only the lane separation first. See how that works, and let people get used to that. In our studies in the US, we already implemented some of the turbo roundabout aspects. So as you can see in the right top and the right bottom, these are two intersections in Jacksonville, Florida, where we evaluated the turbo roundabout design. The top one should be getting built, but there is some delays. On the left one, we implemented the turbo roundabout concept in the designs, and we designed two turbo roundabouts in a corridor of a few miles. And this is a FISSIM simulation of it to help the client also show the public and the investors how a turbo roundabout looks and how it works. Well, that's basically everything I wanted to show you. A lot of information, maybe not all new, but some new. Probably, maybe. Let me see, maybe you have some questions, or we can have a discussion about the aspects, the things we showed, or maybe new topics.
We do have a question. Hold on. Okay, let's try that again. What has been your experience with the rock pavers used for the truck apron in the center island?
What our experience is pretty good. It's where we normally put them is inside this of kind of aprons in the. Okay, I think I'm not sure. Okay, where we use them is in the axle of the corners and in the entry lanes. Also in the center islands we can use them. What we see is cars actually not using them. They see it's not beneficial to ride over. It's hard to ride over, and trucks it's easy. They can almost ride over everything. So using those rocks, as you call them, you can design your turbo roundabouts a little bit smaller to reduce the speeds, but still be able to take the bigger trucks.
This next question just says fewer crashes or less severe crashes or both?
We see both. At least we see fewer severe crashes. Lower speed means also less severe crashes. but in general, it's lower crashes in total.
There was also a question earlier about a sign that was in your presentation. It was towards the beginning of the presentation that was in the middle of the roundabout. It was a yellow sign and it was not in English, and we had a question about what it would be translated to.
Let me see which sign you mean. I think that means that was the sign at the infield. What we showed over there was that it's a warning for the elevated lane separation. So that's a warning for example, motorcycles, that they have to watch out that they're not crossing the lanes because there is a elevated lane separation.
That makes sense. What about a cost comparison between just striping a spiral inside a roundabout as opposed to constructing it with the lane separators?
Yeah, of course, just using striping does do the trick a little bit. It's cheaper. I'm not really familiar with the total cost of the difference between striping or just using, striping or do the lane separation with the elevation. We know that in Germany or other countries, they don't use the elevated lane separation and they just use the striping, and we see different crash rates. So if you look at the investment costs, it's a little bit more expensive. But if you look at the life cycle cost and take a look at crashes, less crashes, I think you can say that using a elevated lane separation is beneficial. But it's a little bit more expensive to build it.
What about the design vehicle for the roundabouts in Jacksonville, Florida?
Yes, I believe that's a normal design roundabout. So they use the radius of 165 feet almost. That is basically based on the right school bus or the WB 40, I think. It is at the entrance of a university at a urban road, so we don't have a lot of truck movements over there. So it's the 165 diameter roundabout.
Okay, we've got two more questions on here right now. Are there concerns that the radial design, wait, hold on. Are there concerns that with the radial design, there is no speed control approaching the roundabout?
Yeah, that's a question we heard a lot of times over here. It's a different type of approach, and we don't see any issues in the Netherlands. With a proper design and a proper warning and a proper signage in the midfield, we see people slowing down. In the US, we are used to do it differently to reduce speeds, and maybe we need to try to design a turbo roundabout with a left offset to have a different approach. We tried to design those, and it's possible to design them. You need to look a little bit differently at entry approach legs and exit legs, but it's doable. So that's what I mean. We need to maybe change the typical Dutch design and make it into a US design or maybe a Georgian design, to make it, to have it have a better fit into the US. Meaning maybe we can do the left offset over here as well.
What about the operational efficiency for more than 4 legs? Has that been reviewed? We as I in particular have not done a comparison, but if you have a intersection with traffic light at the same time, at the same location, you also have a lot of delays and losses by waiting for every direction.
I think that a turbo roundabout at a location with 5, 6, and we even have 7 legs is operational still a benefit. The issue with those bigger roundabouts, turbo roundabouts, is that you need the proper signage, and that can be a little bit tricky sometimes. That's also why I suggest not starting with those in the US.
Makes a lot of sense. How can we preserve U-turn capabilities with these spiral/frogs?
Well, the U-turns, as you, I just showed the Ohio corridor. That's a 2-mile corridor with a median, and we provided the basic shape turbo roundabouts in the right direction, so the U-turn is possible. You have to take the full roundabout, of course, and that doesn't influence the frog. But if you place them right, you can make that U-turn. Of course, capacity-wise, as in every roundabout, making a U-turn costs a lot of the capacity, but it's possible. It's not possible to have a U-turn on all the directions for the basic shapes. Then you need to have the rotor roundabout. That's a little bit bigger. But the basic shape roundabouts, as we used in the Ohio design, are capable for U-turn movements.
The last question I have right now is, what type of material is used for the frogs, and are they precast?
Yes. In the Netherlands, we build a lot of turbo roundabouts. So basically, all elements you saw, the frog, the lane separated, even the infield, that's all prefab. So it is concrete built in in just a factory, transported. So it's easy to use.
Well, that is all the questions that have come in through our chat box. Jaap, I want to thank you so much for being our speaker this month over the webinar series for our monthly meetings. And also thank you to our sponsor again, for Jacobs, for sponsoring this meeting. Please remember to all the people that are attending that you needed to register in order to receive a PDH. If you haven't registered, you should still be able to do that on our website. Are there any last questions through the chat before we end our meeting? Doesn't look like it. Thank you everyone for attending. We hope you guys stay safe and happy and sane, and we'll see you soon.
Thank you. Bye-bye.